So solution stoic and specifically titration analysis is our theme. So I want to make sure mentally you're connecting this to solution stoic before. So we could do some stoic with acid-base chemistry. Hydrochloric acid could react with sodium hydroxide. I'm not going to write the products, but that's a one-to-one reaction. The H from the acid will pair up with the OH from the hydroxide and make water, and you'll get sodium chloride. We're going to be doing something really similar. Okay? We're going to use the same chemicals. The only difference is going to be significant figures. Okay? So we're just doing solution stoic, but with high precision. Okay? Any university wet chemistry is going to do titration analysis. Okay? You need to be familiar with the names of all the equipment that's about to be presented and sort of why we use them and clean them and some of the technical points. So the first technical point is one of the chemicals is going to be up above in the burette. Okay? So you need to be aware that the name of the titrant is burette. Okay? Now, there's where I've labeled the word titrant. Okay? So key vocabulary. Titrant is just one of your reactants. It's what you're adding, and that's in your burette. Your other chemical is going to be called the sample. Okay? It doesn't matter which one goes which. There's no rule. So I've got hydrochloric acid and sodium hydroxide in my intro. One of them is going in the burette. One of them is going down below in the Erlenmeyer flask. It can be either way. We're just mixing the two chemicals until we get to what's referred to as the equivalence point. That is the point where our balanced chemical equation is true. Okay? In this particular case, it would be a 1-to-1 ratio. We don't use the word equal because equal would imply the same, and sometimes our equation is a 1-to-2 ratio. So the equivalence point is when you have the ratio of whatever your chemical equation says. Equal, if it's 1-to-1, equal amount of moles, okay? Or 1-to-2, 1-to-3, 2-to-3. Okay? So titrant, sample, first key bit of vocabulary. Now, when we mix most acids and bases, and we want to stop at this equivalence point, we're kind of in trouble. There's no way to see it. We can't tell when the amount of acid we've added is exactly the amount of base that we had in solution. It's an invisible point. So we need something to tell us that we've hit this 1-to-1 ratio, and 1-to-1 ratio in terms of moles. So we have a few options. We're going to use colors or color change in Chem 20. We're going to have to add a chemical in that's going to tell us that we've neutralized our solution. Okay. We're going to use acids and bases, so we can use a change in pH to tell us that we've used up all of one of our chemicals. So if we had an acid in our Erlenmeyer flask, so we have an acid down below, the pH would be acidic as long as we have some acid left. Once we've used up all that acid, we're going to flip almost instantaneously from maybe a pH of 4 up to a pH of 7, 8, 9, 10. And there are lots of indicators, you've used indicators already that will change color based on their pH. Okay? And that's what we're going to use. Something that we're going to use phenolphthalein for your first lab that is clear when it's in an acid, and when that acid gets neutralized, it's going to turn pink on us and tell us, okay, we hit that equivalence point, okay, which would be right at pH of 7. When the moles of acid and the moles of base have neutralized each other, it's not acidic or basic anymore. Okay. You could, in post-secondary, potentially use a pH meter instead of a color to tell us. So if you had a pH meter and you hit 7 on the pH meter, it would tell you at the equivalence point. Or you could potentially use connectivity. If you were getting rid of ions or forming ions, you could potentially use that data to tell you when to stop. So that's the setup. It's just solution stoic. We're using glassware that gives us lots of sig figs. Okay. The burette up above can read to 2 decimal places. So its volume is going to be a number dot tenths and hundreds. Okay. So that's the benefit of the burette. They're hard to clean. They're this narrow tube. So in order to clean them, we just rinse the burette with whatever chemical we want to put into it. So we're not going to try to fill it with water and put paper towel or anything down the middle. If you're going to put sodium hydroxide in the burette, you're going to run a bunch through it. Rinse everything out that could be in it, any contaminants. After you've rinsed maybe 5 mils through, you can fill it up. Okay? So we don't clean burettes and then fill them. We put the chemical we want into them. Our sample down below, the Erlenmeyer flask doesn't give us any measurements. We're going to use a pipette, okay, to put that sample in. Okay. Pipettes nicely let us put in the exact same volume every time, so we can do repeated trials. Okay. We can use a 10 mil pipette, which reads to 2 decimal places, pipe in 10 mils of sample, do a titration, get our data, okay, rinse our Erlenmeyer flask, pipette another 10 mils, do it again. In science, we want to do things repeatedly. It helps us figure out whether there was systematic error or it helps us reduce random error. So you may want to make a little note in your book about these 2 types of error. Okay? Random error is sometimes high and sometimes low. It's random. Okay? This would just come from any time you make a measurement, the device could be a little bit high or a little bit low. And if you do repeated measurements, the highs and the lows will average themselves out. So with repeated trials, you should get closer and closer to the correct value as you average more data. Okay. So it's just the heart of science is A, experiments should be reproducible, and B, we get more confidence in our data when we average repeated trials. We reduce random error. Now, systematic error is kind of the really bad type of error. Random error is just fundamental to using equipment. Okay? Systematic error would be you pipette and you didn't rinse it very well and there was a contaminant in the pipette. There was a bunch of acid and then you sucked up base and it neutralized 10% of your chemical that you wanted. By doing repeated trials, you're going to see this one trial is 10% low. And you could potentially exclude it. Okay? If you do 4 trials and you get 1.1 moles per liter, 1.2, 1.1 again, and then 0.8, you'd be like, why is this one trial so low? Some type of systematic error must have happened. And you would want to exclude that from your data. Okay? You could spill something, again, contamination. Okay? Putting the wrong chemical in, there's lots of sort of systematic errors you can do. Okay? And sometimes they're more subtle than these sort of big examples that I'm mentioning. Pipettes are great for this repeated trial, okay? Because you can, if you fill these right to the line, you've got this nice 10.00 mils every time. Nice quick repeats, okay? Same math is being repeated through every trial because you have the exact same volume. Graduated cylinders do not give you that repeated volume every time. Now, same with the burettes. You're going to rinse a pipette with your solution. So you're not going to try to just fill these with water and try to dry them somehow, blow air through them. Okay? If you want a acid in here, you're going to suck up some acid into your pipette. You're going to rinse the little fat bulb in the middle and just let it drain into whatever waste you're told to use that lab. Then any droplets inside would be the chemical you want, and then you can fill it up. At the end, we do rinse things with water, but that's just for cleaning the chemicals out. We rinse all our quantitative glassware with the solution that's going in them first. That's our starting point. Okay. Now, reading the volume on burettes is a little different. It's not like a graduated cylinder. You're always going to have two readings, and you're going to do a difference between where you started and where you finished. So the very top of the burette has a 0 volume, and most high school ones, you can't go past 50. They're 50 mil burettes. So 0 at the top, 50 at the bottom, and they have all of these markings for 0.1 mils. You're going to have to read, like you're used to, the bottom of the meniscus. So that red line might be the meniscus on the burette, and you must read down, okay, not up. There are milliliter markings on the burette. So if I start with the ones place, I am past the 0 with my red meniscus, but I haven't made it to the 1. So we do not have 1 mil, we're still at the 0. Reading down. Then we're going to count the little ticks to get our tenths place. And we're past 1, 2, we're past the 3rd tick, going down. So that tells us our tenths place. Then we're going to guess on the hundredths. And you don't even have to agree with your lab partner. It is a guess, but you should be close. So this meniscus is below the 3rd tick. It doesn't even look halfway. It's somewhere before halfway down, and maybe you think it's, 2/10 of the way down between the 3rd tick and the 4th tick. Okay? This is our uncertain digit. That is our last significant figure, and we're not 100% sure. It could be a 1, it could be a 2, it could be a 3, maybe even a 4. And this is the heart of significant figures. We know that's a 3. There's no doubt that it's below the 3rd tick and not at the 4th. Okay? Okay. This question mark digit, and it's always true of significant figures, that last digit is the uncertain one. That's just how significant figures work. And our burettes read in milliliters. Okay? So we would take a volume initial before we start the titration. When you're all done and you hit the equivalence point and you added an equivalent amount of moles of both chemicals, you'll have some V final. Maybe it's 11.42 mils. Okay. You're doing the same type of reading technique from the top down, and the actual volume used is going to be the difference between these two. Okay. The volume of your titrant is going to be the V final minus the V initial. Okay. We don't have to do this with graduated cylinders. We don't have an initial and a final. Okay, but with burettes we do. And then we can potentially run another experiment. You can put 50 mils into these. So if you started just below the 0 and you ended up at 11 and a bit, you could do another experiment. You could go from that 11 down to maybe 21 or 25. Okay, so don't refill your burette after every experiment. Think, do I have enough volume in the burette to do another sample? Okay? And in this case, with the numbers I put up, that is 11.10 mils. So we would have absolutely enough room to do another roughly 11 mil experiment. Okay? We actually could do several more experiments. Okay? So we're going to go and do some math shortly with what the calculations look like with solution titration analysis.